Okay, good afternoon. Let's continue on the gear design. Okay, so we'll try to finish the gear design today. So I'm going through this gear design using an example. There are a lot of parameters, a lot of factors involved, right? But the bottom line is we're using that AGMA equation, okay, which has a lot of parameters. Okay, so this is the equation we're using it here. Right? You have an AGMA equation. So what we're going to try to calculate is we're going to try to calculate the bending stress and contact stress. Okay, and in the previous lecture we have gone through a number of factors already. We have gone through the K naught, KV, KS, KM, KB factors. Okay. I want you to settle down in here. Okay, so we have gone through a number of factors already. We find a WT. Okay, so for this particular equation, right? For this particular equation, we're basically only have this G factor at here. So the G at here, this is called a geometry factor, right? So essentially the G factor here, right, is the Lewis form factor. It's not a completely equivalent. I probably would say it's modified. Okay, so modified Lewis form factor. Okay, so that's the J here. There are different ways of calculating the J, but in our case, what we're going to do is we're going to calculate J factor using a figure set here to help us with the calculation of the J factors here. Okay. Okay, so here is the figures that you're going to use to calculate the J factor. Okay. This is basically figure 14-6 in the textbook. In the textbook, if you look at this figure in the textbook, notice that at the bottom here, okay, there's a key information. First is identify what pressure angle this figure is for. Okay. This figure is for pressure angle 20 degree. In our design project, the pressure angle will be 20 degree. So in my lecture notes, I give you another one which is for 25 degree. Our textbook has only one figure which is for 20 degree at here. Okay. So if you for any other occasion, if you're using 25 degree, then you use this figure at here. So how do I use this figure to find the J factor then, right? There are basically two clusters of curves. One cluster curve is over here, and then there's another one single curve over here. So if you read the footnote here, for this cluster of curves, it says it's a load applied at the highest point of a single tooth contact and sharing. Okay, so basically it's assuming the load is applied. Okay, at the highest point, you have a gear, the force which is applied to the tip of the gear tooth. Okay, sharing essentially meaning assuming there are more than one pair of gear teeth in contact with each other. Okay, but this one, bottom one here, assuming there's no sharing. So no sharing is an extreme case, or it's a low quality case. So if you have a backlash, okay, in the gearbox. And when the two gears are in contact with each other, because the backlash, so you may end up with, you think there are more than one pair of gear teeth in contact, but there's probably just one teeth actually in contact. So that's that type of situation. Okay. So what we're going to use this cluster of curves here for our purpose. So here's how you use. First, identify the pressure angle. Second of all, okay, so you have a pinion, you have a gear, right? So we're going to be able to find two G values, one for the pinion and one for the gear. So to find either one of them, the bottom row at here is the number of teeth, which is basically number of teeth for the gear or the pinion that you're trying to find the J value. And then let's see, for example, right? In our particular case at here, we have a pinion 22 and a gear 60. So if you look at this figure at here, so let's say I'm looking for is J for the pinion, right? First of all, and then we're looking for J for the gear. Okay, so that's basically what we're looking for. So that when you try to find the J for the pinion, okay, so when you coming over here, find the 22 first. So 22 is roughly in the middle between 20 and 24. Okay, then you go up, okay, until you find the 60, number 60. Okay, for the mating gear number of teeth. So there's no 60, but there's only a 50 and 85. So you can roughly, it's a very close curve. So you can roughly basically find a value between the two curves. So if you go 22 up to somewhere here, right? 85 is the second curve from the top. 50 the third curve from the top. So if you're 22 over here, so then you go all the way to the left. So that's approximately around 0.35 in this case. Okay, so that's how you basically find the JP at here, which is 0.35. Remember, this is from figure 14-6. Okay, 14. Is it figure -6? Yeah. And that's JP. So let's take a look at the J value for the gear. The number of teeth on the gear is 60. So there's a 60 right here, and then 60 goes up until 22. So this side you need to find the 22 at here. So this 22 is roughly above 17 and below 25. So it's between 17 and 25. Then you go all the way to the left, and that gives you a value between 0.4 and 0.45. And this is approximately below the middle of the line here. So I would use basically 0.42. Okay, for the JG. So that's the geometry form factor J here for the pinion and the gear. Okay, so bottom line is, if you recall that Lewis form factor, you know, the fact about the Lewis form factor is, as you have more number of teeth, then you will have a higher number of Lewis form factor value. So this one here will share the same trend. The higher number of teeth, the bigger value J would be. Okay, and J value. Okay, if you look at the J value here, it's on the denominator, right? It's on the denominator here. So basically means as you have a higher number of teeth, the bending stress supposed to what? To go down, right? To go down here. So that's the trend. When you have a higher number of teeth, then you reduce the stress, the bending stress. Okay. So this is the JG here. Okay, that's the JG value. Okay. So now if you look at the number of factors here, so we're able to calculate the bending normal stress now. Okay, the bending stress. So basically we already find all the factors that are here. So I can calculate the stress. So let's calculate this bending stress. So we're going to look at for both the pinion and the gear, right? Okay. So let's denote that as sigma p. Okay. Let's see. Let's denote that as sigma p and the sigma g. You don't need a bracket actually for the bending stress at here. Okay. Sigma for the pinion, okay, is Wt, Ko, Kv, Km, Kb. And then there's a size factor. Now size factor is the difference for pinion and the gear. So if you recall that as a different value. And then diametral pitch divided by face width, and then 1 over that geometry factor, Jp. So those numbers we calculated in the previous lecture, Wt. Diametric pitch is given, which is 6. Okay. So phase width we also derived, and then we use the 2-inch and the JP, which is this. So substitute everything into here, and you get 6,809.2 psi. Okay, so that's the bending stress on the pinion at the root location, the pinion teeth. Okay. Similarly, you can calculate sigma g. The only difference between sigma g and sigma p is this size factor, and also the jg value added here. Okay, so the geometry factor. So this one will give us a value of it's not very clear. .6710.67 psi. And up to here, you get the bending stress for both of the pinion and the gear. Okay, yeah. So once we find these two, and the next step, we'll find the contact stress, and then after contact stress, and what we do is we're going to have to find the allowable strains. Okay, yeah, and then we'll compare the stress with the strains to figure out the safety factor, basically. Okay, yeah. So I'll show you in an Excel file the template for calculating all of these things here, okay, to save you some of the tedious calculations. But for now, at least for the current assignments, number 5, I want you to go over the hand calculations, just get more direct experience or impression with respect to all the different AGMA factors that are here. Okay. Yeah. Okay. So the next step, we'll look at the contact stress. Okay. We'll look at contact stress on the surface of the pinion and the gear there. Okay. So if you recall in the previous lecture, okay, we decided to use a simple model to represent the contact stress on the gear surface or pinion surface to the surface, and that model is called the Buckingham equation. So if you recall that Buckingham equation, basically it's a sigma C equal to Cp at here, and then Wt over F times dg at here, and then 1 over cosine phi t, let's call it cosine phi, okay, sine phi, okay, over 2, and mg over mg plus 1, and then 1 over 2, okay, and then Cp, okay, so this is called Buckingham. Cp is called elastic coefficient. Cp is basically Cp is a long equation. Cp is basically 1 over pi, and then 1 over 1 minus. Okay, so that's basically what the so-called Buckingham equation. Okay, this Buckingham equation is the basic equation for calculating the contact stress. Okay. So if you compare this Buckingham equation with the equation given for the AGMA contact stress equation, okay, essentially it's pretty much the same thing, except that the AGMA equation added a few number of basically factors added here: KO, KV, KS, KM, and then CF. Right? It does have on the numerator, on the denominator, there's a parameter called I. So this I at here, okay, this I at here is basically this chunk. Okay, so this chunk at here is the I. Okay, this is the I at here. So the I at here, this I is called surface strength geometry factor. Okay. This is the I, surface strength geometry factor. Now we're not only just designing for spur gear, okay. So in this section here, we can easily extend every formula that we used to helical gear, okay, to helical gear. As a matter of fact, actually just reminding myself now, I'm gonna have to go back to the G factor to talk a little bit about the helical gear. Okay, let me finish this first. Yes.
Mg is the absolute gear?
Oh yeah, mg is the gear ratio.
Oh.
Yeah. Okay, mg is the gear ratio, and the phi at here is the pressure angle, right? Okay. So Vp, Vg are the Poisson's ratio, Ep, Eg are the Young's modular. Okay. Yeah. So Cp at here, this is called. Okay. We'll look at the next after elastic coefficient. Okay. Elastic coefficient. Phase race, and then this is not a dg here. This should be the dp. Okay, this should be dp. Okay, so dp at here. So this is the pinion pitch diameter. Okay, pinion pitch diameter. So dp is the pitch pinion pitch diameter. Okay, the pitch circle diameter. Yes, right.
For your contact pressure,
yeah.
you have mg over mg
plus 1. Yeah. It does look like h. Yeah. Okay, so what I write, the one I write, I wrote that here. It's not a complete AGMA equation. It's the basic AGMA equation, which we call the Buckingham equation. So AGMA equation, basically you add a whole number of factors over here, right? You know, basically those KO, KV, KM, and then KS. Okay, so that's complete AGMA equation. Okay, yeah. But the format essentially is the same format though. So let's come back to the surface strength geometry factor. Okay? So surface strength geometry factor, which is this expression, basically this expression here. Okay? Now this expression is for definitely for spur gear. Okay, it works very well, no problem at all. Okay, but for helical gear, so we need to make a slight modification. Okay, yeah. So instead of using that equation here, I will write slightly different expression for the I. It's actually not quite a difference. Okay, so now we'll define the I as this. Basically, we'll take helical gear into consideration. Okay, so this is the new formula for the I factor, the surface strength geometry factor. Okay, surface strength geometry factor. So if you compare with that simple equation, the Buckingham equation, what's the difference now? The gear ratio is still there, so no change. And the symbol used to be phi, which is pressure angle, right? So now this is a phi t. So phi t at here, we call that transverse pressure angle. Okay, transverse pressure angle. If you remember when we learned the terminologies for helical gear, and I mentioned that helical gear, you have two set of parameters, right? One set of parameter is in the transverse plane, and the other set of parameter is in the what? The normal plane. Basically, the helical gear, the tooth is not straight. And if you look at it, the front view of the helical gear, that's transverse plane. If you cut it using a normal plane, which is normal to the helix, okay, to the helical curve for the gear tooth, then you get a normal plane. So in two of these planes, you get basically two different gear parameters. You have a pressure angle in the transverse plane. You have a pressure angle in the normal plane, basically. Okay. So this phi theta here is called the transverse pressure angle. Now, for spur gear, you only have one set of plane. So when you have a spur gear, when you look at the front view, right, it's basically the transverse plane, right? So if it is spur gear, so this phi t will be the same as the spur gear pressure angle, basically. That makes sense, right? So the symbol-wise, it doesn't really conflict. It just include more information now, right? Yeah. And in our case, it's a 20 degree, right? Ours is a spur gear, so there's a 20 degree in our case. Okay, yeah. There's another parameter here called Mn. Okay, there's Mn at here. So the Mn, I mentioned a little bit at the end of the previous lecture when we talk about the G factor, the geometry factor. So this Mn here is called the load sharing ratio. Okay, so the terminology called is load sharing ratio here. So what you do is you will let it equal to 1 for spur gear. Okay, and then if you're designing helical gear, okay, you have basically a different formula at here for the spur gear, and that formula is Pn over 0.95Z. Okay, so this is the formula. I don't need you to go into too much of the details here. So let me show you what Pn is, what a Z is. There's a bit of a expression, a long expression involved here. Okay. Okay. So Pn is basically the normal base pitch. So basically it's the pitch value, okay, circular pitch value, okay, for the base circle, along the base circle. And in which plane? In the normal plane, right? So helical gear, you got two planes, transverse and normal plane. So this one here is in the normal plane, circular pitch value along the base circle. And it's related to basically the circular pitch in the normal plane, and then also the pressure angle in the normal plane by this value. Z here is the so-called basically the contact length. If you remember when we learned the terminologies, there's one called contact length. So that's the maximum basically contact length. So when gears start to engage and then disengage, so that much of the distance traveled is this contact length. The formula for contact length calculation is also given over here. Okay, so all of this have been coded into the Excel. So if you're designing if you choose helical gear for your project, there is an Excel template for the helical gear. Okay, so you don't need to worry too much about the formulas, typing right or wrong for the formulas, right? So that's basically the difference, okay, between the basic equation and the equation in the AGM here, and that's I value right here. Okay, so you see in our particular case, we have mg here, which is 60 over 22. Okay, so and then our phi t is 20 degree, and mn is 1. So you substitute all of the values over here, you'll be able to get this I value. Okay, the I value here. So we get our I value, which is 0.1176. 1176. Okay, so for contact stress, the I value doesn't differentiate between the pinion and the gear. So you get the same value basically for the pinion and the gear. All right? Yeah. So remember, there's no IP or no IG. It's the same thing, just the one I value. Okay. And then if I look it back to the equation here, I also have the elastic coefficient. Okay. So elastic coefficient that here, it's very easy to calculate as long as you find the Poisson's ratio and the Young's modular for the based on the material of the pinion and the gear. Okay. So our material, so basically CP here is called elastic coefficient. Okay. And for this particular calculation, okay, there are two ways to calculate. Okay, so first method, right, is using the equation. Okay, so which equation? This equation here. Okay, we use this equation to calculate. So if I use this equation, then I need to find Poisson's ratio. So this from appendix A-5. Appendix A-5, you'll find the Poisson's ratio and the Young's modular for typical material. So you're going to find, because we're choosing cast iron, we can find that the Young's modular, of course, cast iron for both pinion and gear. So the Young's modular will be the same, which is 14.5 times 10 to the power 6 psi. And also the Poisson's ratio, okay, can be found to be 0.211. So then substitute those values into the elastic coefficient formula, and you can calculate CP. Okay, so you can calculate CP, which is 1544. The unit is a square root psi. Okay, square root psi. So this is from formula. This first method, and that's how I code it into the Excel also. Okay, for you to do the calculation. So let me show you the Excel here. So CP is over here. So that's the CP. Where did that formula go? Interesting. Anyway, so that's where the CP is. Formula over there. Okay. So you look at the geometry factor I, so that's the formula definitely. That's there, right? That's there. Okay. Yeah. So you can take a look at this one here. Okay, so that's the first method. And the second method here. Okay. Second method here is to use a table. So you can use table 14-8. Okay, 14-8. I'll show you what this table is. So here is 14-8. Okay, so this is 14-8. 14-8, how to use it? One column here is the pinion material. The row at here is a gear material. So let's say we want to find a CP. So what we can do is looking for the material for the pinion, which is cast iron. Look for the material for the gear, which is also cast iron. And then these two intersect at this point. So that value there, okay, is basically the CP value. So this CP value here is 1960. So that's slightly actually different from the formula calculated based on the formula there, right? So 1960. So this table, the table is not a very accurate calculation, but it's one way to quickly identify basically the values for the CP. When you do the design, okay, it doesn't matter whether you use this formula or choose the table. You know, it's up to you. That's okay. Okay, yeah. It shouldn't change too much in terms of the design. Okay, it does change the CP value though. Okay, so that's the CP. Okay, so good. So now if you look at the contact stress, if you look at the contact stress formula, So we so CP is calculated, I is calculated, KO, KV, KS have already calculated from when we calculate the bending stress. So we have a Km at here. Km is also calculated, and then we have a CF, right? It's the only one that remaining at here. Okay, so we're almost there. So basically, once you finish the bending stress, and this part is actually not too bad. I really wanted to go back a little bit at here, okay, to the G factor. I think I missed one point I wanted to mention at here. The G value, okay. So in this particular example, we use a spur gear, right? You might want to choose a helical gear for your design. If you use a helical gear, then the G value, finding the G will be slightly different, okay? So how you find the G value when you have a helical gear is this, okay? So you're going to use two figures. One is figure 14-7, another is the figure 14-8, okay? So for helical gear, okay, use figure 14-6 and 14-7. Okay. So how do you use these two figures, right? You look at the two figures here. This is how you use it. Actually, 7, 8. 7, 8. Okay. Use these two figures to find the G value here. Okay. So if you look at the two figures here, what it means is the first figure is 14-7. This is, they call it the geometry factor G prime. 14-8 is called the G prime multiplier. So basically, whatever value you find from the 14-8, you use that value, multiply the value find from 14-7. Then overall, will give you the G value, okay, the form factor. So, for example, if you're using the helical gear, then there's a one parameter for helical gear is the helix angle. So basically, how inclined the helical teeth is on the surface of the cylinder, right? That's helix angle. Okay. The helix angle, often in time, it's up to the manufacturer. Manufacturer doesn't necessarily produce, all different varieties of helix angles. So if you buy off the shelf, you probably will have a limited choice there, basically. Okay, yeah. So find the helix angle first. Let's say it's 20 degree. If the gear has 30 teeth, so then you go 20 degree to 30 here, and that gives you this G prime factor. Okay. Then you go to the next one here, use the same thing. So 20 degree, 30 teeth, you got the multiplier factor, which is this much. Then you multiply these two together, then you get this G value. Okay. So that's basically for helical gear. So helical gear G equal to G prime times this G prime multiplier. That's basically how you find the G value when you're dealing with helical gear. So for the pinion and the gear, you're going to find the two different values for the J, right? As same as spur gear, so the higher the number of teeth, then you would have basically higher number for the J value. Okay. Okay, so that basically is for the J by considering helical gear. Okay, so let's continue it here now. Now we have just one more factor for the contact stress, the CF factor, which is called surface condition factor. Okay. Surface condition factor, it's not a very complicated factor here. As a matter of fact, so let me see, do I have a slide here? Yeah. So this factor here essentially by taking the surface finishing conditions into consideration, residual stress, plastic effects. Okay. So for most of our examples or applications, we can consider standard surface finish, and we'll just basically use one for this particular factor CF. Okay. Yeah. So that's CF. And so basically we'll consider CF to be 1 for for entire examples in this class at least. Okay, CF will be 1. So now we're ready to calculate basically contact stress now. Okay, so let's calculate contact stress. We'll call it sigma C for the pinion. Okay, so it's Cp times Wt Ko Kv Ks for the pinion, the alignment factor Km, surface condition factor, dP, which is the pinion pitch diameter, face width, the geometry factor, strength, okay, I at here, square root. Okay, so remember, it doesn't really matter whether you're calculating the contact stress for the pinion or for the gear. So this dP here is always dP. Okay, you actually don't change this to dP or dG when you calculate pinion or gear. So substitute everything into here, you get 46842 psi. Okay. And then you can calculate sigma C for the G, for the gear. Okay. Very much the same formula, except one difference. Okay, so for the contact stress between the pinion and the gear, the only different parameter is this. Okay, it's this one here. That's the only difference. Then you can calculate this one, which end up to be 46995 psi. Okay, that's right. Sigma C, okay, because the KSG at here, okay, is bigger than the KSP, because the gear typically will have a larger gear tooth size. So you should have this relationship for the contact stress between the pinion and the gear. Okay, so the gear contact stress should be bigger. Yes.
Why is the elastic
The table, if you look at the table here, let me see, do I have the footprints? Okay, yeah. So in the table, it used the Poisson's ratio as a constant 0.3. So it didn't differentiate. You see, when I use the formula, I use the Poisson's ratio 0.211, right? Yeah. So that's one of the reasons. You know, it's trying to simplify the situation, I guess. Yeah. Okay, that's one of the reasons. Good. So now we got two different types of stresses: bending stress, contact stress, right? For the two different type of failure that we want to analyze. So once you find the stress, so the next question basically is, so what do we want to compare to, right? So you got the stress, then you had to compare the stress with a certain type of strength value to make sure it's safe. So that's basically the next stage. What do we compare with? So what we're going to compare with, the so-called the strength value. Okay. So here are two formulas. Okay. One formula is for the strength value for the bending stress. We call that ST prime. Okay, and the formula for the ST prime is this. And then the other one is the strength value for the contact stress. We call the SC prime, and that formula is this. Okay. So here are two basically strength formula. So let's just call that strength formula. Okay. So if I look at this strength formula here, then again there are a number of factors involved here, right? So let's go through these number of factors that are here, okay? And then I'll explain what exactly are these things that are here. Okay? Yeah. First of all, the SCST. Okay, this SCST here. Okay, they're called stress number. Okay, stress number. Yeah. And ST, the subscript ST, that's for bending. SC, that's for the contact stress, stress number. So how do I find the stress number then, right? There are a number of figures in the textbook that you can use to find the stress numbers. Okay, so I'll show you a couple right here. So this is a figure 14-2 and a 14-3. So these two figures, okay, they will give us the ST value. So for example, so I'll write down something here. So for example, right, 14-2 and 14-3 give ST value. Okay, that's one. Actually, there are a couple of tables also give ST, but that's one example here. So how do you use this figure? For example, look at if you look at the footnote in the figure here. So actually, sorry, 14-3 is called contact strength. Maybe I should look at. I'll show you the figures from the textbook. This is better. Okay. So this is 14-2. So 14-2 at here give you the allowable bending stress number for through hardened stress. Okay, for through hardened steels. And the 14-3 give you allowable bending stress number for nitrated through hardened steels. So there's slightly different basically surface finishing at here, surface process at here for the 14-3. So how you use this table is very simple. Horizontal axis is the hardness. Vertical axis is ST. There are only two lines here, one for grade 1 steel, one for grade 2 steel. Then if you choose grade 1 steel, then your ST is calculated using this formula here. Okay, so you're going to have to identify yourself a hardness. Let's say you choose hardness of 200 or 300. Then substitute it in this formula, you'll get the ST value. And this ST value, of course, based on this 14-2, that's for the type of material which is a through hardened steels. Okay, yeah. Is that good? Right, that's how you do. As a matter of fact, this is the one I restricted you as a one possible material for the gear, okay, in the course project. And the other possible material is the cast iron, I believe. Okay, yeah. So if you choose this one, you'll get a slightly different value, of course, right? Yeah. And if you look at figure 14-4, okay, it's still allowable bending stress number, but there's basically a different type of basically steel with the alloy, right? Table 14-3, okay, will also give you this bending stress number ST. Okay. First row is the through hardened. That's where you refer to the figures. And then there are a few number rows at here for different basically type of materials here. And then you find the values over here. Okay. See, that's the idea to find the ST and SC. If you keep looking down here for SC, so we do have SC here. So 15-5 is for the SC now. So that's the contact fatigue strength SC. Similar usage, okay. And table 14-5 is also for SC. Okay. 14-6 is also for SC here. Okay. And there might be another one. Maybe not. Yeah.
Is this file in the Connect?
This is in the textbook. Yeah. But
it's not a Connect.
I can upload to Connect. Yeah. So I just take out a few pages from the textbook. Yeah. So the idea is basically, I think I should see. Yeah, that PowerPoint has a little bit mistake here. This shouldn't be 14-3. It should be 14 probably -5. Okay. So the idea is essentially to use those figures or tables based on the choice of material for the gear or the pinion. Okay. So I do want to mention one thing though. Okay, I do want to mention one thing. So actually we'll come back to this one here. If you look at the subscripts of the tables here, okay, and also the titles of the table, they all say this. This is the strength value at how many cycles? At 10 to the power 7 number cycles, and 0.99 reliabilities. Okay, so basically the table of the value here, okay, same thing for here and here, okay, they're based on the certain test, which is 10 to the power number 7, okay, 10 to the power 7, and also based on the reliability of 0.99, okay. If your design if your design have a different number of cycles, like our examples, we'll see that, okay, other than just 10 to the power 7, if your reliability is not 0.99. So that's where the other parameters come into the picture to modify this situation for you. Okay? Yeah. And there's also another thing before we move on here, just want to be clear is, now if you recall that in the fatigue loading, design for fatigue loading, and we learned, you know, one thing is how to calculate endurance limit, right? And the formula for endurance limit is SE equal to KA, KB, number of factors, and then the SE prime. That look familiar, right? Yeah. SE prime at that part of chapter is called uncorrected endurance limit, or the lab condition value, and this is corrected, right? So unfortunately, the symbol here, right, when it comes to the gear, you see, the primed one becomes the corrected. The non-primed one becomes this uncorrected. Is that okay? Right? So don't get confused yourself in terms of symbol. Okay? This is basically the difference that is here. Okay? So you can call this is uncorrected, and you can call this side here is the corrected. Okay. So that's the difference. All right? Yeah. So coming back to the example we have here, right? We have a cast iron. Okay. So from cast iron, let's see for the contact for the bending stress. For the bending stress, so I'm going to use this table 14-4. So this is a bending strength ST number. So the first row is the cast iron here. Okay, cast iron. And I guess I didn't really see what class it is. Actually, yeah. So I think the question here says class 40 probably already. Right? Is it class 40? Yeah. So cast iron class 40. So if it's cast iron class 40, if you look at the table from for this one here, and from table 14-4, okay, and you get the ST value right here is 13,000 psi. Okay, 13,000 psi. And we also need the SC value. So this one here, we're going to use the table 14-7. So 14-7. I missed one table. Anyway, there should be another one here. Yeah. So you can take a look at 14-7 to find SC there, which is 75,000 psi. So that's ST and SC value uncorrected for cast iron. Okay, that's just basically a stress number, okay, for this one here. Okay. And then for both of the equations here, there's a common factor KT and KR. So what's KT? It's temperature factor. Okay, temperature factor. There is a formula for the temperature factor, but in this particular question, we didn't really specify any temperature though. Okay. So, where's my temperature? Yeah. Okay. So this is a temperature formula you can use. Okay. Yeah. For temperatures up to 250 Fahrenheit, just use a 1. Otherwise, use this formula for the temperature. Okay. So 255 Fahrenheit is very high temperature. So most probably you're going to use 1 for the KT. And then KR right here is the reliability factor. Okay, reliability factor. reliability factor. For this one here, you're going to use table 14-10 to look for appropriate KR here. So this is table 14-10. For 0.99, it's 1. I think in our particular case, we're using 0.9 as a reliability, so our KR will be 0.85. So that's KR. Okay. So you're looking back here. So we find the bottom two factors. Okay, and we have the numerator yn and zn in here to figure out. So let's take a look at what the yn. What's yn? What is y? What is the z and here? Okay, what is z? So yn zn. Now, if you recall at what I was just talking about for those figures here, right? Those values are based on the 10 to the power 7 number cycles, and also based on 0.99 reliabilities. Then, if you're operating at number cycles for the life number cycles other than 10 to the power of 7, then you had to apply this yn and the zn here. So this guy here, they are basically called stress cycle factor. Okay, and of course the yn is for bending stress, and the zn is the same factor, but this is for contact stress. Okay, so that's what yn and zn's are for. Okay, so how do I find yn zn? I'll show you. There are two figures we can make use of to find yn and zn. So here's a figure dash 14-14. Okay, so figure 14-14. So yn, figure 14-14. Okay. And in this particular figure here, okay, if you look at the bottom here, that's basically the number of cycles. Number of cycles 10 to the power 7 is over here. Okay, below 10 to the power 7, and then for different harness, for different material, surface finish, you have a different basically formulas. At 10 to the power 7 here, okay, it kind of branched out, okay, to different to only two lines at here. So one is this line, and the other is this line here. So if you have a number of cycles that is above 10 to the power 7, you can literally choose either the top one or the bottom line here for the yn calculation. In my formula for the Excel, I choose the top one here, okay, for calculating yn. The reason is if you look at closely, when you substitute 10 to the power 7 into the yn, you get exactly 1. Okay, exactly 1. So basically, your yn value, okay, you can choose that. Basically, it's true the same as what I did, which is the formula for the top line there, which is this formula here. Okay, that's your yn. And then for the zn, okay, for zn here, there's a similar figure you can use for zn, and this is basically zn here. That's 14-15. Very similar. At the 10 to the power 7, it crossed the 1, and beyond that, you got two lines here. Okay, one is this, one is that. So we'll choose the same thing, the top one here for calculating zn. So zn here is 14 dash what is it? 15, and zn is 1.4488. Okay. That's how you calculate this zn. And all you need to do is substitute the actual number of cycles into the formula, then you get your yn and zn. For this particular example, okay, I think it's already given to you, assuming a pinion life of 10 to the power of 8 number cycles. Okay. Now, in your course project, you probably actually have to calculate a little bit based on some given conditions. For example, what's the RPM, how many hours life you want your system to spin, right? then you'll be able to calculate the total number of cycles. So in our particular case, okay, n is equal to 10 to the power 8 for pinion. Okay, then yn for the pinion. Okay, yn for the pinion is just substitute this 1.3558 10 to the power of 8, and then like this. So that equal to approximately 0.977. Now you also need the yn value for the gear. Okay, yn value for the gear. So unfortunately for the gear, the life is not 10 to the power of 8 anymore. So if the pinion has 10 to the power 8, then how many number cycles will be for the gear? What do? The gear ratio, right? Yeah. So in our case we call mg. Okay. So very good. And that gives us approximately 0.994. Okay. Yeah. So similarly, you can calculate Zn for the pinion and the Zn for the gear. Okay. So this one will be this much. This one will be here. That's the stress cycle factor. Okay. So in of the two set of parameters, okay, for pinion and a gear respectively. Okay, so the last factor here, okay, last factor is a CH factor. CH factor is called harness, basically correction ratio here. So I'll show you what this one here. That's CH. So it's called the harness ratio factor here. Now CH will be only used for gear calculation only. Okay, so look at the red color here. If you're calculating the stress number for the pinion, you don't need a CH. It's only for the gear. The reason is because it's always pinion, right? Technically, it's always a pinion pushing the gear, and the pinion typically, okay, and you choose the material of the pinion or the surface finish of the pinion to have a higher harness than the gear. Okay? And so that constant pressure application from the pinion to the gear, okay, that process basically will give you this kind of work hardening process on the surface of the gear. So that's why this factor here will be only used for the gear. And the formula is given in 14-36. Okay? It's purely based on a ratio between the harness for the gear, the pinion, and the gear. Okay? So if this harness ratio is between this much, then you use this value here. Okay? If this harness ratio is less than 1.2, let's say you choose the same material. If you choose the same material for the pinion and the gear, then this CH value will just simply be 1. Okay? Yeah. So in our case, right, of course, we choose the same material for both pinion and gear, so that'll be 1. Okay. So this is just a factor that bear in mind. You know, often in time, you probably the harness between this pinion and gear won't be too much of a difference. But just bear in mind there is this factor here for you to use. Okay. Okay. So once we have all of this factor here now, so we can calculate what is the corrected, okay, bending stress number. Okay. So you get your ST prime for the pinion. You get this much, 14,942. And then you get your ST prime for the gear, 15,202 psi. And similarly, you can get your corrected contact stress now. So we call that stress number, but it basically is a strength value. So SC prime for the pinion, 83,647, and SC for the gear, which is 85,676. Okay. So you've got your bending stress number, you've got your contact stress number. Finally, you can look at the safety factor. Okay, so safety factor, we use SF in this section here. We use SF for bending, so that's a safety factor for the bending. Of course, you're going to calculate the bending for both pinion and gear. So SF for the bending here, right? This is basically ST prime for the pinion divided by the bending normal stress at the pinion teeth, and this is approximately 2.2. And SF for the gear will be ST prime for the gear over sigma for the gear, and that gives 2.66. And finally SH. So SH is another safety factor. This is the safety factor symbol we use for contact stress calculation. Okay. So this is SC prime for the pinion over sigma C for the pinion, and this gives us 1.82. And SH for the G, which is SC prime for the gear, and then sigma C for the gear, 1.86. So that's basically the results for this particular analysis question. You end up with a safety for both contact stress and the spinning stress. Okay, so they're all greater than 1, so it's safe. So is that clear? So that summarizes the bigger picture here. There are a lot of parameters. Behind each parameters, there are a number of resources, figures, or tables that you use, or formulas that you use to do the calculation, right? Yeah. So this is where I want you at this stage to get familiar with this template. This is a template I give it to you guys for your design project. The template, the idea is for the shaded cells, they're supposed to be the entry value, so they're given values basically. And the other lighted cell, so they are essentially supposed to be the calculated value. Okay, yeah. But somehow, someday, maybe something got screwed up. May not be that consistent, right? But overall, that's the idea. So if you look at this Excel, the number of factors for the gear, AGMA factors, they're all over somewhere over here, and the number is over here, right? See that JPJG. So there's some number of factors that you have to manually enter it because there's no formula you can use to calculate. You have to manually enter it. Okay? Most of them will have a formula for you to basically calculate. Okay? One of the common errors I have seen, at least for your design project, common error, is the number cycle calculation. Okay? So some group very carelessly, I don't know why, but basically they didn't calculate number cycle correctly. And you can take a wild guess. You make a mistake at it here, I don't need even to look at your project anymore because the rest of the calculations are going to be all wrong, right? So you got to be very careful in terms of the calculation. Okay? Don't let me catch a mistake like this kind of obvious ones. Okay? Yeah. Because the system you're designing, okay, is a basically completely coupled system. Okay? And I think I'll talk about this in the next lecture when I roughly finish the shaft parts. Okay, yeah. So very possibly, and actually not very possible, it is must. You will actually design first, design that. You will actually go back to look at the gear again. Okay, so it's going to be an iterative process. So and you could be lucky, say, going one step here. Oh, everything works, perfect, right? Yeah. But the whole design process I'm looking for is more or less of a see if you are iterating at it here to show that you have taken things into consideration. You have basically closed loop. Okay, looking at the design process. Okay. So that's basically the design for the gear. Yeah. There's two diagram here. You can take a look at yourself. Basically, what's the flow of the charts for analysis? What's the flow of the chart for design? Okay. So very different. Very different. For analysis, it's pretty much one-way direction. right? Based on the given parameter, calculate, get the results. It's a yes or no for safety. But for design, it is basically definitely a iterative process. And for design, it's often open-ended. It's not like one set of parameter will work, and there's probably another set of parameter will also work. So the question for you is, you should make a rationale. Why do I choose this set of parameter but not that set of parameter, right? Yeah. Not that your rationale is absolutely right, but if you show that, then I'm happy to see that. Okay? Yeah. So take a look at this one here yourself, right? Yeah. Okay. So I still have a little bit of time. So I do want to, while we're still kind of on the same topic of gear design, and since there are so many different parameters added here, so I do want to go over roughly some of the effect that we can see. Basically, what's the effect of AGMA factors when it comes to the design? Okay. Yeah. So bottom line is, okay, you have your equation. I gave it to you guys right here. These 4 equations. Okay. So we're going to look at. So you have the spinning stress equation, contact stress equation. You have the stress number for the bending, stress number for the contact stress. Okay. Yeah. So what we wanted to do is basically, if I keep or change certain parameter, what's the effect on those AGMA factors? And ultimately, what is the effect on the stress set here? And then finally, we also wanted to look at this another case. If we don't have all the information, so how do we start the design, right? Yeah. Okay, so this part here, let's call that basically. So effect of AGMA factors, okay, on stress, okay, on stress. So let's go over the first one. Take a look at quickly the first one here. Okay, the first one here, I'm going to assume in this scenario, you have the number of teeth for the pinion, and then the number of teeth for the gear. Okay, now we're going to keep them constant. So we're not going to change the number of gear teeth and pinion. Okay, so they're not going to change. What we're going to change is we're going to change this diametral pitch. Okay. So let's make it to one direction. So let's say we're going to increase. We're going to increase this diametral pitch. See, that's the point, right? You know, for the gear design, I did not specifically tell you the number of teeth you should use, and I also did not tell that specifically the value for the diametral pitch, but I do give you a number combination like a 2, 4, 6, 8, or 12, I don't know, right? The number of options there. Okay. Yeah. So the point basically is you have to bear in mind, you know, what are these numbers effect here is. So let's see if we do this. Okay. So what are we gonna see in terms of the effects on the stress here? Phase width value. Phase width, if you recall, we have this empirical equation. Okay. So diametral pitch, let's call that PD. So this is the empirical equation for phase width. It should be within this range at here. And you can see now, if you change this PD to be bigger, or if you increase the PD, so that basically means the F value will what? Will decrease, right? Will decrease. So you will end up with a smaller phase width value. So F will be smaller. F will be smaller, and then what are other things? Let's look at the gear ratio. Gear ratio is the ratio between the number of teeth for the gear and number of teeth for the pinion. Now we're not changing them; they are being kept the same. So this one not changed. Horizontal line, arrow representing no change. Okay, so no change here. If you look at the bending stress equation, you have the geometry factor J. So J here is the form factor. So it's basically Lewis form factor, right? I think in the previous lecture I used the software to show you. If I keep the number of teeth, but increasing this or decrease the diametral pitch, the gear tooth form, the length will change, but the gear tooth form will actually be kept, the geometry form will be kept the same. So you'll see, you won't see any physical change in terms of the geometry form. Okay? So basically the G value will not change if you keep the NPNG the same. Okay? So that's this part here, right, for the G. And then the pitch diameter, okay, dP and dG. Okay, so dP, so basically in general d is equal to number of teeth divided by the diametral pitch. If n is not changing but PD is bigger, so that basically means the dP and the dG will be smaller, right? Will be smaller. Okay. And then Wt is a horizontal transmitted load, okay, transmitted load, and Wt is equal to the torque divided by the pitch diameter, okay, pitch diameter. So the torque on the pinion and the torque on the gear will be different, but the ratio between T and D will be the same, Wt. And torque comes, of course, calculation based on the horsepower and also transmitting angular velocity. So T will not change, right? T will not change. And D, as we just showed here, D is decreasing. So that basically means the Wt will what? Increase, right? Will increase. Okay. So as you increasing the P diametral pitch, you get bigger transmitted load. Okay. Yeah. And there's another one that's pitch velocity. And V is pi dn over 12. So as you can see, V depends on the pitch diameter. If pitch diameter is decreasing, then the pitch velocity will decrease. Okay, will decrease. And then you have the load factor KO. So this one, there's no effect. It shouldn't be any change. Velocity dynamic effect factor KV, and that is related to the pitch velocity, pitch line velocity. So if V is decreasing, then the KV will decrease. KS is the size factor. So size factor here, if you recall, that KS formula is this formula. Okay, this is the KS factor. This is the formula for KS. So you look into the formula here, you have a Lewis form factor Y. So Y will not change, right? If you keep the number of teeth, Y will not change. And PD, as we just look at it, PD is going up. And F is what? Going down. So this is smaller, this is bigger. So overall this size factor should decrease, right? To decrease. So, and finally there's another one here is the misalignment factor Km. Km, this one is a little bit complicated, but because it does involve a few more factors. This is original formula for Km, and the CMA is equal to A plus BF plus CF square. So CMA depends on the phase with F. So if F goes down, then CMA will go down, right? Will become smaller. And CPF, okay, if you recall that CPF depends on the ratio for F and pitch diameter, pinion pitch diameter. Okay, so F goes down and dP goes down. So it's hard to say. This is ratio right here, and then there's also the ratio square in the formula for the CPF. Okay, but if you look at our Excel, you can try yourself. So the overall CPF value will tends to go down. Okay, as the diametric pitch is increasing. Okay. Rim thickness factor. So we can assuming no change. So I basically assume no effect on that. Okay, no effect. So with all of this one here, we can summarize. Okay. Basically, for now, it's NP and NG, okay, fixed, and PD increasing, right? PD increasing. And summarize basically WT increase, V decrease, DP and DG is decreasing, KV decrease, KM going down, and KS going down, J no change. Okay, so overall, right, you look at, well, there's a lot of factors going down. There's only one factor going up, right? There's probably an impression that the stress for the bending, okay, and the C here probably go down. Actually, you'll see that it's actually going up. The WT plays a very important factor in the stress calculation. Okay, yeah. So overall, you'll see an increase in the stress for the bending and the contact when it is under that situation here. Is that good? Yeah. So I will stop here, but there's another case I want you to consider yourself. I think I'm going to skip this case from the next lecture here. Another case is basically you fix PD and then you increase the NP and NG, and then the gear ratio you keep it. The gear ratio you keep it the same. Okay. So fix PD, increase both the pinion and the gear teeth number, but fix the gear ratio here. Okay. So if you do this, you'll end up with your sigma for the bending and the contact will go down. Okay, will go down. So higher number of teeth will end up with less stress. That's definitely a fact that you should remember. Okay. Any questions? Okay. Good. Yes.
Do you have extra handles and latches? Next slide.
Okay. All right.